All right, let's talk about something that trips up pretty much everyone in machine learning, the bias-variance trade-off. It's one of those core ideas you absolutely have to get your head around to build models that actually work. So let's jump right in.
So, we've all been there, right? You build a model, you feed it your training data, and the scores are perfect. You're thinking, I've nailed it. But then you deploy it, you show it some brand new data, and it just completely falls apart. It's so frustrating. Why does this happen? Well, the answer lies in this really delicate balancing act.
So here's how we're going to break this all down. First, we'll look at the two classic ways a model can fail. Then we'll meet the real culprits behind the scenes, bias and variance. After that, we'll see how model complexity is our control dial, why there's always a trade-off, and finally, how to find that sweet spot. Okay, first up, let's talk about the symptoms. When a model's performance is off, it's usually suffering from one of two classic problems, overfitting or underfitting.
On one side, you've got overfitting. Think of this as the student who just memorizes the practice test. They know the exact answers to the questions they've seen, but the second you rephrase a question or give them a new one, they're totally lost. On the other side is underfitting. This is like the student who, well, didn't study at all. They failed the practice test and the real exam because they never grasped the basic concepts to begin with.
And this quote just hits the nail on the head. The real danger of overfitting is that your model isn't just learning the important patterns, the signal. It's also memorizing all the random, meaningless stuff, the noise, that just happens to be in your training set. And that noise won't be in any new data, which is why the model fails.
But here's the thing. Overfitting and underfitting are just symptoms. They're the fever. To really understand what's going on, we have to look at the underlying disease, the two types of error that cause these problems, bias and variance. So, let's start with bias. And I should say, when we talk about bias in machine learning, it has a very specific technical meaning. It's all about a model's assumptions. Basically, you can think of high bias as your model being too simplistic, maybe a little bit stubborn. It makes really strong, rigid assumptions about the data. It's like trying to fit a straight line to a data set that's obviously a complex curve. By being too simple, it just can't capture the true patterns, and that right there is underfitting.
Okay, so if bias is about being too simple, what's the deal with the other side of the coin, variance?
Well, variance is the total opposite. A model with high variance is way too complex and flexible. It's so sensitive that it doesn't just learn the underlying signal, it bends and twists to fit every single random point and bit of noise in the training data. Then, the moment you show it new data with different noise, its predictions are all over the place. And that is the textbook cause of overfitting.
Okay, so high bias leads to underfitting, and high variance leads to overfitting. So the big question is, how do we get a handle on them? The key is to think of your model's complexity as a kind of dial you can turn up or down.
It's a pretty clear relationship when you look at it like this. If you turn that complexity dial way down, you get a simple model, which means you're in high bias, underfitting territory. But if you crank that dial all the way up, your model gets super complex, and you're heading straight for high variance and a huge risk of overfitting.
And this constant push and pull between bias and variance, between a simple model and a complex one, brings us to the fundamental challenge that everyone faces in machine learning.
This is the heart of it, right here. There's just no free lunch. You can't have it all. As soon as you start to reduce the bias in your model, you almost always increase its variance. And if you try to reduce the variance, guess what? The bias starts to creep back up. It's an inescapable balancing act.
Think of it like a seesaw. Let's say your model is underfitting, so it has high bias. You decide to make it more complex. Maybe you add more features. Great, the bias goes down. But what happens on the other end of the seesaw? The variance goes up, and now you risk overfitting. The goal is never to completely eliminate one, because you can't. It's all about finding that perfect balance point.
So if it's a trade-off, what do we actually do? How do we find that sweet spot where our total error is as low as possible and our model actually works on new data? Well, let's get into some practical strategies.
First, and this is absolutely critical, you have to split your data. Use one part for training, another part, the validation set, for tuning your model, and a final untouched test set to get a true, honest measure of its performance. Second, be smart about your features. More isn't always better. Sometimes just throwing everything in is a recipe for disaster. And third, use powerful techniques like regularization. This basically adds a penalty for complexity, which encourages the model to be simpler and helps keep that variance in check. So let's bring it all home. What are the big takeaways here? Just remember, overfitting and underfitting are what you see. They're the symptoms. The root causes are high variance and high bias. The knob you can turn to control them is model complexity. And the ultimate goal is not to get rid of one or the other, but to find that perfect balance between them.
And this all leads to a really interesting final question. What really makes a model the best? Is it always the one that gets the highest accuracy score, or is it sometimes the one that we can actually understand and explain? You know, a slightly less accurate but simpler model might be way more useful in the real world than a complex black box that nobody can make sense of. It really depends on your goal. And that's our look at the bias-variance trade-off. If this explainer helped clear things up for you, I'd really appreciate it if you hit that like button, share it with anyone else who might find it useful, and subscribe for more deep dives like this. Thanks for watching.